ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at kinetic molecular theories of gases, or in other words, KMT. KMT describes the relationship between those four variables that we've discussed: the pressure, the volume, the number of moles, and the temperature of gases, and really gets into the molecular behavior of what the gases are going to do. Now, we're going to start off with some basic assumptions of the model. And so the assumptions is something that you definitely want to get down. So the first assumption is that all particles in a gas are in constant random motion. And so let me say that again. So all particles in a gas are in constant random motion. First assumption, everything's moving, nothing is stationary. The second assumption, so that would be the first one. Notice I'm not writing these down, but you definitely need to. The second assumption is that all collisions between particles are perfectly elastic. And so what that means is that anytime a gas molecule collides with either the side of the container or with other molecules, it's a perfectly elastic collision, which means the gas molecule that's involved in the collision is not going to lose any energy in the process, all right? If you really want to think about it and get technical, according to this kinetic molecular theory, or KMT, my gases can gain energy, but my gases are not going to lose energy through those collisions, all right? Okay, number three, the volume of the particles themselves. So the volume of the gas particle itself, we understand that molecules have atomic radii, right? Is that we ignore those. So the volume of the particles in a gas is negligible. We're going to ignore it. So the volume of the particles in a gas are negligible. We're going to ignore it. Number four, the assumption number four, the average kinetic energy of the molecules is its Kelvin temperature. So the average kinetic energy of the molecules is its Kelvin temperature. So a couple of those we've actually heard before, right? Number four, for sure, that's the heat 'em up, speed 'em up idea that we've been talking about for so long. All right? Now, one thing you definitely want to know is that the theory does ignore a couple of things. It ignores and assumes that intermolecular forces between gases do not exist because the gases are so far apart in three-dimensional space, right? And the other thing that it makes the assumption of, and this is true anyways, is that the gases will expand to fill any container that they are put into. All right, so if I take a gas and put it down in the corner, again, we saw this in our last videos. If I insert a gas right here, right, put gas molecules there, it won't be very long before those gas molecules actually expand to fill the entire container. All right, okay, so now let's look at the kinetic molecular theory in action. We're going to look at a couple of different scenarios. All right, so hopefully you got those notes and you got all of those assumptions down. So scenario one, what we're going to do is we're going to look at the pressure-volume relationship, and we are going to hold constant number of moles and temperature. All right? And so in this particular case, I'm going to give you an equation here. This is the ideal gas law equation. I'm going to pronounce it as Pivnert. And so what I want you to understand, if I hold temperature and pressure constant, then this side of the equation is a constant. Now, R is equal to the ideal gas law constant. And what it is a constant. Just like you would think of any other constant in any other equation, it's a constant value. It's something that's going to be given to us we can plug in. So if I keep number of moles constant, I keep temperature constant, my gas constant. So all that multiplied together is a constant number. And so now we understand when we take a look at this, if I increase the pressure in any particular system, in order for the other side of this equation to remain constant, volume itself will have to actually decrease. And so again, if you've been having trouble reasoning this qualitatively through our demonstrations or through some of the demonstrations that we will see, the mathematical explanation of this actually is probably going to help quite a few of you along, right? So the pressure volume have an inverse relationship because of the way that this equation is designed, in the fact that if I hold one side of this equation constant, that means these two, if one gets bigger, the other one has to get smaller, right? And so if the volume is decreased, let's look at a different scenario. Oh, this is the same scenario. If the volume is decreased, that means the gas particles will hit the wall more often, and thus it will increase pressure, right? And that should make sense to you. I give them less room to move around in. They hit the side of the container more often. My pressure is actually going to go up. And so that would be scenario 1. Scenario 2, what we want to take a look at is what happens if we are going to vary volume and temperature, and we are going to hold constant, I'm having trouble spelling today, the number of moles and all right, and so what we're going to do is we're going to start out with the same equation. We're going to start out with PivNert, and we're going to do a little bit of rearranging, a little bit of creative rearranging here. Since I'm going to keep pressure constant, I'm going to go ahead and make this my constant value. So notice I just divided off pressures, and what that gives me is that volume equals to some constant and temperature. And so now what we understand with this, if I'm going to increase volume, I'm going to increase temperature. These variables don't change. These are held constant. So just reasoning out the idea that whatever's held constant, I'm going to combine, right, will show you the direct relationship between volume and temperature. And so it really gets into the fact that the volume changes in order to keep pressure constant most often. So when a gas is heated, in this particular case, if I heat a gas, the speed of its particles increase, right? They hit the walls more often and with more force. So the only way to keep pressure constant is to increase the volume of the container. And again, ladies and gentlemen, if you're having trouble with understanding conceptually and describing what's going on, it will not hurt you to write down verbatim what my explanation is for the particular scenarios that I'm doing, right? And so again, when a gas is heated, the speed of its particles increase, and they hit the walls more often and with more force. So the only way to keep the pressure constant is to increase the volume of the container. And we see it very easily quantitatively in this particular case, right? If I increase temperature, this is constant, volume has to go up. All right, and so now let's take a look at scenario 3. Right? And scenario 3, what we're going to do is we are going to take a look at our pressure-temperature relationship. We are going to hold constant our number of moles and our volume. So again, start out with the same PivNert equation, and this time I want to combine my N and my V, and so I end up with P equals NR divided by V. So again, this remains constant equals temperature. Well, I'm in the same boat with this as I was in the last situation, where if I increase temperature, I've got to increase pressure if I'm going to hold volume and number of moles if this all stays constant. And so again, logically seeing it from the equation is relatively simple, and so let me go through and actually just verbally explain what this is. So when the temperature of a gas increases, the speed of its particles increase, right? The particles are hitting the wall with their greater force and more often. So since the volume remains the same, this would result in an increased pressure of the gas. So again, let me say that again. When the temperature of a gas increases, the speed of its particles increase. The particles are hitting the wall with greater force and more often. And since the volume remains the same, this would result in increased pressure. Okay? All right. So here we go. Moving on. We are burning right through this. Scenario 4. In this particular case, I am going to vary volume and number of moles, and I'm going to hold constant, in this particular case, my temperature and my pressure. So again, start out with the same PivNert, the same ideal gas law. I'm going to combine my temperature and my pressure, and so what this ends up looking like is I get volume is equal to, not N, because I'm varying that. So that would be RT over P, right? That's what's held constant, is directly proportional to N. So again, holding this constant, we see that if I increase the number of moles of gas, I should increase the volume as long as pressure is going to remain constant. And so again, let me verbally say that. An increase in the number of particles at the same temperature would cause the pressure to increase if the volume were held constant. So the only way to keep pressure constant is to increase the volume. All right? So again, an increase in the number of particles at the same temperature would cause the pressure to increase if the volume were held constant. So the only way to keep pressure constant is to increase the volume. All right? And so those are four big scenarios for us, ladies and gentlemen, that relate these four variables. The other one we'll get into, and it's the understanding that pressure of individual gases actually combines into be partial pressures, but that's something that we'll get into later on, ladies and gentlemen. Right now, I would be completely ecstatic if you understood the relationship between pressure and volume, between volume and temperature, between pressure and temperature, and between volume and the number of moles of gas, and could explain those on a molecular basis according to kinetic molecular theory. All right? If you got questions, get them down. I'll see you in tutorials for those. Otherwise, I will see you in class.